All right, this is our last section from chapter 21. So 21D, we're going to look at optimization. This is another application of the derivative function that we can use to help us solve problems. Typically, we're going to use this. The first example is going to be looking at profit for a company, and then we use it a lot with optimizing geometric shapes, like optimizing packaging for a company that produces cans. They want to optimize their shape so that it's most economical for them to make. And so we're going to look at how that works. So the first one says for the cost function, they give us this cost function and revenue function, both in dollars. Find the production level that will maximize profit. The profit is equal to the revenue minus the cost. Maximize profit. So we take, this is how much money we bring in minus how much money we spend, and that gives us our profit function. So we're going to write our profit function. I'm going to call it P of X. The profit's going to depend on how many items we make. So if we make one item, we'd plug it in, and that'd tell us the cost to make one item. If we make 50 items, we'd plug it in and tell us the cost to make 50 items. Same thing here. If we make one item, it tells us how much we make. If we make 50 items, it tells us how much money we make, how much revenue we get. So our profit's just the revenue from a certain number of products minus the cost to make those products. So I'm going to take R of X minus C of X, my revenue minus my cost. So my profit is equal to, my revenue is 15x minus 0.002 x squared. I'm going to take away the cost, 720 plus 4x plus 0.02 x squared. So my profit function for this, we'd have to distribute the negative into those parentheses. Minus 720 minus 4x minus 0.02 x squared. We're going to put our like terms together. Let's see. So we've got, I'll show you my calculator so you can see what I'm doing. We're going to put our x squareds together. Negative 0.002 minus 0.02. So negative 0.022x. Let's see. That'll be 11x. That's squared. 11x minus 720. So this equation gives us our profit based on producing an X number of items. So if we know however many items we can produce, if we plug it in, it'll tell us how much money we make off of those items. So the first question says, find the production level that will maximize profit for, and we have a restriction. So this says 0 is less than or equal to X, which is less than or equal to 200. What that means is the number of products we can make in a certain day or week or whatever this is, the number of TVs or boxes or whatever we're making that we can make is between 0 and 200. So this might be due to labor restrictions, how fast our equipment works, that type of thing. We're restricted. So we can only make between 0 and 200 items for this example. So I want to figure out what value here gives me the most profit. Graphically, I think is the best way to look at this. We can do the derivative function, but very rarely do you need to. Almost always you can use your calculator to help you with this. So I'm going to graph this, negative 0.022 x squared plus 11x minus 720. Not much is going to show here. I've got very big numbers. We know that our x has to be between 0 and 200. So on my window, I can change my x to 0 to 200. For my y's, we're dealing with this 720. I'm not really sure. Why don't we just graph it like that and see what happens. See if we can see it. Oh, there it goes. So it looks like it's going up. And I don't know what happens after that. So we definitely want to see further up. So maybe we go from, I don't know, what would we try 200 maybe? Scale it by 10s. Let's see how that looks. All right, looking better, looking better. So let's continue to scale our y-axis. Maybe we go up to 1,000. We just kind of play around with those numbers until, oh, there it goes. Okay. Now there's part of the graph that's kind of missing down there, so on my window I'm going to change my y to negative 720, so 800, make that positive 800. I think that's going to make a nice looking graph. Looks nice to me. You can see the whole line from left to right. So what this is saying is if we make 0 items, if x is 0, we lose money. Specifically, we lose $720. If we make this number of items right here where it crosses the x-axis, we make $0. We break even. And if we make more than that, we start to increase in how much money that we make. If you look at your table, if you make no items, you lose $720. If you make 1 item, you continue to lose money. And you can scroll through your table. It takes a while. But you can scroll through your table and see, okay, where do I make $0? So where do I break even? Might be a question that you could be asked. So let's see, we're getting closer and closer, 70, 60, we're getting close. There we go. So somewhere between here and here, right? At 77 items, we lose $3.43. At 78 items, we make $4. So right in between 77 and 78 items, that is where we break even, okay? And we can make between 0 and 200. If you notice, it just continues to go up. So our profit, it just keeps increasing. It all the way, let's see, I think it increases all the way to 200. So that's bigger, 350, 360, 370, 380. We're making $400. Keeps getting bigger and bigger and bigger and bigger and bigger. So for this interval between 0 and 200, our best bet to make the most profit is going to be right here at 200 items. Whenever we make 200 items, we make $600, which is bigger than any other profit that was between 0 and 200. So we can use our So we use our graphing calculator to find the maximum value for this function, which is our profit function, on the interval of 0 to 200. We can't make more than that for whatever reason, and so the answer here is we have a maximum profit of $600 at 200 items when x is 200. So that's right here. When x is 200, we make $600. So that's going to be our best bet. Now for part B, the thing that changes is they change our interval. So find the maximum profit between 0 and 350. So maybe we've upgraded our software. We've gotten more people to work for us. Something has changed where now we can produce up to 350 items in a day. And so something different happens on this interval. So I still have it graphed from before. I'm going to go to my window. I want my x to go all the way up to 350 this time. Now we can make more items. Let's see. Kind of make some of this scaled a little better. So, what happens? This is our profit function, so this is the amount of money we make. We've already taken away our cost. This is actually money we get to keep. So it goes up, 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 up. We're making negative money. Right here we make no money. We break even. Then we start producing items, and we keep making more and more and more and more. And at some point, it turns around and we start making less. The reason it might turn around is you might have to start paying overtime at some point. And so overtime is going to cost you a lot of money. Maybe you have to work through the night. So you have to pay people for that, or your equipment might, at a certain point it starts to break down. So if it produces too many in a day, it gets worn out and it breaks down. So you might, lose some money at some point. So we need to find this point, because between 0 and 350, our maximum profit is not at 350. Our maximum profit is up here before it starts to decrease again. So in our table, there's a potential that we can find it. So there was our 200 items. Notice if we can make 201, our profit continues to increase. At some point, it's going to turn around and start to decrease. So it's still going up, 650, 651, 652, 64, keeps going up. Oh, and there it is. Okay, so now it's going back down. So somewhere in this range, the 255-ish range, it turns around. The way to get the precise from your graph is go second, calculate. We want to calculate a maximum. This is where you have to do the left and the right bound. So I like to put my cursor all the way where I think the maximum is. But I don't press any buttons besides that. And I go to the left because it says left bound. I'm going to go to the left quite a bit. It doesn't really matter how far you go. Enter. I'm going to go around, across, over the hill, back to the right side. Now I'm going back down, so this is a good point to press enter. Enter. And there it is. So, this here, we use graphing calculator. To find maximum on the interval 0 is less than or equal to x, 350. So 0 is between, or x is between 0 and 350. And in this case, we're actually going to get a maximum profit right there. So our max profit is $655 when we produce 250 items. So this is a matter of using the buttons in your calculator, knowing how to scale your window, knowing how to use your table to find values, and so it's kind of a graphing calculator technique. We could do this using a derivative. So at a maximum point, our slope is 0, so we could find the derivative, set our derivative equal to 0, and solve, but that is considerably more work, and I'm all about efficiency. So this is perfectly fine for this class. It's perfectly fine for your IB exam as well. All right, question 2 says, a 4-liter container must have a square base, vertical sides, and an open top. So square base, vertical sides, open top. Okay. So a picture would probably be given to you on your IB exam. This container holds 4 liters. That is a measurement of volume. Has a square base, so all the sides of the base are equal in size. Has vertical sides and an open top. Find the most economical shape, which minimizes the surface area of material needed. I'm going to call this X down here. That's the side length of my square base. I'm going to call this H. That's the height of the shape. Find the most economical shape, which minimizes the surface area of material needed. So if this holds 4 liters, 1 liter is 1,000 centimeters. So we can say 4 liters. We do a unit conversion because 1 liter is 1,000 centimeters cubed. And so this would hold 4,000 cubic centimeters. So instead of 4 liters, we can use 4,000 cubic centimeters. It wants us to minimize surface area. So surface area is all of the areas of the faces added together. It doesn't have a top. So if we call the base X, then the area of the base is X times X. Okay? And there's only one base. The top is open. The area of each of our vertical sides is X by H. And there are 4 of those. So our surface area is going to be equal to 4xh plus x squared. This would be x squared. This would be 4xh. That looks like another x. That should be multiplied. So this is an equation for the surface area of that shape. We want to minimize it. So to minimize the surface area, we have multiple variables. We have a height, we have a height, and we also have a x value here. So we're kind of stuck. All right, well, we know something about our shape. It holds 4,000 centimeters cubed. That's our volume. So a volume formula is for a rectangular prism is volume equals length times width times height. So our volume here equals x squared times h. Our volume is 4,000 cubic centimeters. It gets a little tricky here because we have to get down to one variable. We have two equations with two variables, and we want to get down to one variable. So something I noticed is with my surface area formula, this is what we want to minimize. I have x's in two spots, but I only have an h in one spot. So it's going to be easier to replace my h than it is my x, because x is in two different spots. So I'm going to come over to this formula for the volume, and I'm going to solve this for h. So to solve this for h, we divide by x squared on both sides. So h equals 4,000 divided by x squared. Now we can take this and plug it in over here. So my surface area is 4x, h is 4,000 over x squared plus x squared. Now we have an equation that only has one variable. So we have our surface area, which is a variable, and then we have this, which is in x's. I'm going to simplify this a little bit. Wouldn't necessarily be required, but this x would cancel with one of those, and the 4 times the 4,000 is 16,000. This is what we want to minimize. So let's graph it. We want to find the minimum value for that function. So y equals, I'm going to graph 16, you guys like to use alpha y equals, I know, so I'll do that. 16,000 over x plus x squared. I'm probably going to change my window up a little bit because I have it all changed from my last problem. So I'm going to zoom 6 and see where we need to go. Alright, can't see it, so why don't we zoom out and see if we can get an idea of where our line, oh, there's part of our line. Alright, that doesn't really help. Let's try changing our window up a little bit. See how that works. Something that we do know is we know that our x has to be positive. We can't have a negative side length. Our surface area is also going to have to be positive, so when we go to our window, we don't need negative x's and we don't need negative y's. My y maximum, let's change it to something a lot bigger. I'm having a hard time finding it. Let's see. Maybe we can look at our table. So when all else fails, we can go to our table. There's an error at 0. We're looking for a minimum. We want to minimize our surface area. So look, we're up there at 16,000. This is why I wasn't able to see it. Look how big these numbers are. So we want to minimize, get smaller and smaller and smaller. And that right there is the smallest it reaches on the table. It's good to double check that that's the same on the graph. So we're up here at 1200. So for my window, my y's, that should cover it. For my x's, we only got to 20, so why don't we just do 30? Woo, there it is. All right. So my table helped me find this a little bit. Helped me kind of narrow down what my range needed to be to figure this out. So you can see it kind of turns and then it ends up going back up just a little bit. So to find my minimum, I'm going to calculate a minimum value. It's somewhere in here. So I'm going to go there, over across that to the right. Starts to kind of go back up right there, so that seems safe. Enter, and it should, yep, there it is. And it does give me the value that was in my table. So So what does that mean? So it wanted us the most economical shape which minimizes the surface area. So we have for our base, x is 20. Y is the surface area. So this would go here. We would have 1200 as our surface area. That's the minimum, the lowest we can get the surface area to be. This is the side length of our base, was the 20 and the 20. If we needed to find the height, which typically they'd probably ask for that as well, you would take this, x value is 20, and plug it back in here. So 4,000 equals 20 squared times h. 20 squared is 400. So we would do 4,000 equals 400 times h, divide by 400, and that gives us 10. So the dimensions that minimizes the surface area would be 20 by 20 for our base times 10 for our height. So what did we do? So that was a lot. There was a lot to that problem. So how did we break this down? The first thing we did is we noticed the information they gave us. So they gave us that it was a 4-liter container and that was 1,000 centimeters. So we converted into centimeters. Then we knew the volume. So we set up an equation for the volume. But what we're trying to minimize is the surface area. So we needed to have an equation for the surface area. So the surface area was the area of the base. We had a single base plus the area of your vertical sides, and there was 4 of those. 1, 2, 3, 4. When you add those together, you get your surface area formula. It was in x's and h's, and I just needed x's. So we solved this and plugged it in so that our only variable was x. Graphed it to find the minimum value, used our table and a combination of things on our calculator to find the minimum, and then we plugged it back in to find the other dimension. So our x is 20, 20 by 20, our height is 10. All right, let's try one more question. This question would give you a picture. I just didn't get it snipped over. So a square sheet of metal, 12 centimeters by 12 centimeters, has smaller squares cut from the center as shown, so that's where the as shown goes. So they cut squares from the corners. So they cut those out, and then they fold it up, and it makes a box with an open lid. So this would be the outline of the box. So you would fold, right, you'd fold along here, and along there, and along here, and there, and then tape it together, and this would make a little box. So you cut these little squares out all the way around. They want us, what sized squares should be cut out so that when the sheet is bent into an open box, it will hold the maximum amount of liquid. So we want to maximum amounts of liquid. We want to maximize volume. Okay, so we probably need to figure out the volume of this shape. Let's call each one of these little guys x. So that's the dimensions of the thing that we're taking away. We're taking away a little x by x box, a little x by x square from each corner. If we looked at the dimensions of this, this and this would end up being the same because we took 12 and we cut the same amount. 12, cut the same amount. So these would be the same. And this would be 12 minus 2x because we have to take away both x's. 12 is the whole length, take away 2 x's. So this is 12 minus 2x on both sides. If we imagine folding this up into a box, okay, there's our box. This little height of our box is going to be this length, which is x. And then this is 12 minus 2x by 12 minus 2x on both sides. So our volume formula for this shape is length times width times height. So 12 minus 2x times 12 minus 2x times x. This is what we want to maximize. We want to maximize the volume. We want to maximize the space inside. So I'm going to do a little distributing. 12 times 12 is 144. 12, that's negative 24x, minus another 24x, plus 4x squared times x. So put our like terms together inside the parentheses. 144 minus 48x plus 4x squared times x. Distribute the x. So there's our volume formula, and we want to maximize it. For this question, this is a nice looking formula, so I'm going to show you the algebraic way as well as the graphical way. So the algebraic way is we want to maximize it, so we want to find that point where it goes up and it stalls out, and there's like a maximum point. So to do that, we would find the derivative. So that would be 144, because that's to the first. Drop the squared, so minus 96x squared. Oh, not x squared anymore. Plus 12x squared. Now, this is just kind of icky, because this derivative function is a quadratic, and so it's kind of hard to solve. So instead of doing that, I'm going to go to my calculator, and then I'm going to show you how it works in the derivative function at the end. So I'm going to graph this original volume formula, because that is what I want to maximize. 144x minus 48x squared plus 4x cubed. My window's all messed up from before. We have some restrictions on x that aren't taken into account on our graphing calculator. So first, our x has to be positive. We have to take away at least something positive. And then in addition, our x, since we only have 12 centimeters to work with across the whole thing, and we're cutting off of both sides, x can't be bigger than 6. If x was bigger than 6, right, then you can't cut 7 inches off of both sides of a centimeters. You can't cut 7 centimeters off of both sides of a 12 centimeter sheet. So we can't really cut nothing. So x has to be bigger than 0, and it has to be less than 6. So x has to be between 0 and 6. If I look at my table, when x is between 0 and 6, let's find maximizes the volume between 0 and 6. On my calculator, it shows 2. It shows a maximum of 128 at 2. I can't really see that on my calculator, so I'm going to change my window. So it's saying x can only be between 0 and 6, so that's pretty small, but we were up at 128, so I'm going to look up at 150 and see if we can see that. Okay, so it's a matter of kind of playing with your calculator so you get the hang of how to find what you're looking for. Our x value can only be between 0 and 6, and our maximum value for the volume is going to be up here. So second, calculate maximum. I want to go to the left side and the right side of that maximum point. So the left side is over here, enter, scroll around. This is not a precise thing. You just have to make sure you're on the left and then make sure you're on the right. Enter, enter. And that is correct. That is the point that was in our table, and that is correct. So it says we minimize this, or sorry, maximize. X is 2, y is 128. Y was our volume. X was the side length of the square we cut. So what does it say? What size square should be cut so that when the sheet is bent, will hold a maximum amount of liquid? This tells us that it should be a 2 by 2 square. This value is the derivative finds the slope, and the slope at a minimum point like this should be 0. So if we plug in 2 to our derivative function, it should give us 0. Just trying to show you how all this connects. So if I plug in 2, 144 minus 96 times 2 plus 12 times 2 squared gives us 0. So this value does give us a slope of 0 at that point. All right, thanks for watching. This is the last section of Chapter 21.